So next window is a Hamming window technique. So this Hamming window here, this equation is came from raised cosine window equation. So in that equation substitute alpha is equal to 0.5, you get a Hamming window, okay, WH. So you have to denote Hamming window as HN, window as W. WH of n is equal to, substitute alpha is equal to 0.5 in raised cosine window equation. 0.5 plus 0.5 cos 2 pi n by n minus 1. Here the limits are minus n minus 1 by 2 to n minus 1 by 2. Okay. So now if you find out the Fourier transform of Hamming window, you can get 0.5 sin omega n by 2 by sin omega plus 0.25 into sin omega n by 2 minus pi n by n minus 1 by sin omega by 2 minus pi by n minus 1. So how to get this equation? So this equation you have to follow the steps in raised cosine window procedure. Okay. So now this is a WHN of e power j omega. This is a Hamming window. Now you have to multiply Hamming window with impulse response. Okay. So now you can get a HRN of e power j omega. This is the Fourier spectrum of Fourier transform of HR of e power WHN of e power j omega is like this. Okay. Here the main lobe, the width of main lobe is 8 pi by n. This is 8 pi by n. Here the magnitude response, this is the windowing Fourier spectrum of window in dB, in decibels. Okay. So here this is a minus 50, this the attenuation which came to 31 dB here. So this 31 dB, that means there is less number of ripples in pass band and stop band compared to rectangular window. So here there are less number of ripples. Okay. And this is twice that of rectangular window. Hamming window is twice that of rectangular window. In rectangular window, the value is, the width of the main lobe is 4 pi by n, and here the Hamming window is 8 pi by n. The width is twice. So this is for n is equal to 25. So for n is equal to 25, this is 0 and these are 12 and these are 12 total. N is equal to 24. Okay. This is the Hamming window technique. Okay. So if you consider for n is equal to 51 also, for that here is 24, here is 24 and middle one is 0, total n is equal to 51. Sorry, 25, 25 and 1, 51. Now next window is Hamming window technique. So for Hamming window technique, you have to substitute alpha is equal to 0.54 in raised cosine window equation. So for that you can get WH of n. So here for Hamming window you have to represent it as H. For Hamming, HAMMING. For Hamming window you have to represent as WHN. Okay. So this is a Hamming window, right? So for Hamming window you have to represent only H. Okay. After substitution alpha is equal to 0.4. So you can get the equation 0.54 plus 0.46 cos 2 pi n by n minus 1. Here the n limits are in between minus n minus 1 by 2 to n minus 1 by 2. Okay. So this is the window, Hamming window. Okay. Now the Fourier transform of WH of n is this one, 0.54 and sin omega n by 2 sin omega by 2. And the procedure for finding the Fourier transform of WH of e power j omega, I already told in raised cosine window. So you have to see how to calculate WH of e power j omega. Okay, so after Fourier transform you can get WH of e power j omega. Now, so this is the Hamming window sequence. Hamming window WH of n. This is WH of n. This is WH of n. Okay. Now, in order to get a finite response, you have to multiply WH of n with, okay, so this WH of n you can multiply with HK of e power j omega. Now you can get H of n. Okay, so that is the finite impulse response. So in order to get the finite impulse response, we are using windowing techniques. Okay, so the Fourier transform of Hamming window is this one. Okay, see, so this is the frequency response, normalized frequency response of window, and here the main lobe is 8 pi by n k, and the side lobe, these two are side lobes. This is also a side lobe, and the main lobe is 8 pi by n into k. So compared to Hamming window, here there is some improvement in side lobe. There are some less number of oscillations when compared to Hamming window. So here the magnitude, the phase response, which is WH of e power j omega in dB, which is minus 41 times, reduces the response. That means what? So compared to Hamming window, here the frequency response, the number of oscillations are reduced in both passband and stop band in Hamming window. Okay. Next window technique is Blackman window technique. So the Blackman window, which is represented as WB of n, this is a equation of Blackman window 0.42 plus 0.5 cos 2 pi n by n minus 1 plus 0.08 cos 4 pi n by n minus 1. Okay, so now we have to take capital N is equal to 25. Here small n limits are in between, minus n minus 1 by 2 to n minus 1 by 2. Okay, so these are the limits of small n, and here take capital N is equal to 25. Okay, so WBO of n, this is the Blackman window. Okay, so now here the frequency response. So after Fourier transform of WB of n, you can get mod of WB of e power j omega. See, this is the response, normalized frequency response of Blackman window. Here the main lobe is increased from 12 pi by n. For Hamming window it will be 8 pi by n. And here the main lobe width is increased to 12 pi by n. So when compared to Hamming and Hamming, there are less number of oscillations. That means there is no oscillations in passband and stop band. And here when compared to Hamming and Hamming window, it will be 16 dB improvement. That means, so it will be reduced to minus 57 dB, and here is a 16 dB improvement in Hamming and Hamming window. So in side lobes there is no oscillations. Here also there is no oscillations. Here this is 50, and the peak side lobe level, which is down to minus 57 dB. So this is the magnitude response in decibels.